An electrical motor is a machine that turns electrical energy into mechanical energy. Hi, my name is Dave Kowalski, and I'm going to show you how the interaction between electric current and magnetic field can be used to do that. The device that I put together is an attempt at a simple motor. 2 wires to support the rotor. How I did that, just to give you an idea of what's going on in that loop. Take this solid copper wire, wrap it around here. And then I just stripped the insulation off each of the ends. To create a commutator effect, I painted one side with paint through about 180 degrees of the copper conductor there, so that the other 180 degrees is still exposed copper. And then on the other side, I didn't put any paint, it's all copper. So as you set that in here, and it begins to rotate, you're going to get a commutative effect where through this 180 degrees of turn, the circuit is open or off, no current flowing, and then through this other 180 degrees of turn, have current flowing through the coil. We know from Biot-Savart that the interaction between an electrically generated magnetic field and another permanent magnetic field will result in a force that tends to align the two fields. That is going to tend to align the lines of flux in such a manner that they want to seek this position right here, so that the north is coming through here, going into what I have here is the south end of the magnet. The magnetic field that's enclosed by a closed contour of distance L is equal to the current density flowing through the area bounded by that closed contour of distance L. So what I end up with is a relationship H, magnetic field intensity, is proportional to Ni. What I did is vary the number of turns and try to keep the current pretty constant, and I'm going to show you that the magnetic field created inside the coil increases as the number of turns increases, and I'm going to demonstrate that by the speed at which the motor rotates when it has more turns. Starting with a 30-turn coil, I'm going to demonstrate a property that all of the coils exhibit, the 30-turn coil especially, and that is prior to starting, the current is about twice what the steady-state current ends up being, and the voltage is considerably lower. As I start the coil turning, the amperage drops, the voltage climbs. It's going to fluctuate because the circuit is turning on and off, so what we see on there is basically an average current as a result of the on and off state. I'm going to switch out to a 15-turn coil. Watch as I turn the power on, as the north pole of that electrically generated magnetic field tends to pull itself towards the south pole of the permanent field below it. Okay, hopefully you can see that. And I'm going to help it get started here. Alright, there's the voltage and current that we had before. And very close in speed to the 30-turn coil, but maybe just a little bit slower. Alright, let's move down drastically now to about a 2.5-turn coil. Okay, there's the same current and voltage, but quite a bit slower, with the same amount of current and only 2 turns. Okay, and then lastly I'm going to show you what 1.5 turns looks like. Okay, that's about the same current and voltage, and just quite a bit slower. With the large number of turns and the right current the motor should be able to start itself. Well, I hope you learned a little bit more about the relationship between current and the number of turns in a DC coil.